Okay, what I'd like to do today is I'd like to talk about a concept called um, equivalent resistance in series and parallel circuits. So um, there's a couple layers to this. What I want to do is I want to start by drawing out a basic series and a basic parallel circuit, and we're going to compare and contrast them. So remember, in a series circuit, you've only got one path for electricity to travel, and in a parallel, you got multiple paths. So here I'm going to draw a basic series circuit. I'm going to draw maybe, let's say, well, I'll just do two resistors in series with a battery, right? And parallel, remember I'd have more than one path. So instead of them being on the same path, there'd be like one here and one there. Okay. Now, here's what I want to show you. I'm going to skip briefly to this animation that I've got here. So I've made two series circuits, one that has one light bulb and one that has two light bulbs. Okay, so here's one light bulb, and you can see how fast the electricity is moving. And I want to show you how fast the charges move if I connect two light bulbs. So you should notice two things, right? Everything is identical except that I've got two light bulbs here, but you should notice that the charges are moving slower here. If you need to see that, see it's 2 amps over here, but over here it's only 1 amp, right? So if I added a bulb in series, the current went down. I want to talk about why that is. Okay, so this series circuits are pretty straightforward, but I want to go through it because when we get to parallel circuits, it's going to be a little bit less straightforward. So let's say that I have a 9-volt battery here, right? If I have a 9-volt battery, what I'm doing is I'm saying that everything on this side of the battery has electric potential of 9 volts, right? Everything on the other side of the battery, I don't really have another color handy. I'll just do it in this. Everything on this other side has 0 volts, right? So look at what happened here. When I had one when I had one resistor or one light bulb, that light bulb got the full 9 volts. But in this case, assuming that these are, let's assume these are equivalent resistors, right? What's going to happen is from here to here is not 9 volts. It's probably 4.5 volts. So I only have 4.5 volts between here and here. Okay, so what happens is in a series circuit, right? More resistors makes the current decrease, and that should make sense, right? If it's harder, if you've got more things to resist you, you should go slower. Okay, but something weird happens. I'm going to go back to my animation here. Here I've got a parallel circuit. I'm going to start with. This is just one circuit. Let me turn on conventional current instead of electron current. Okay, so so here I've got one bulb, and look here, I've got 2 amps of current. Now watch what happens when I hook up another bulb in parallel this time. My current went up, right? And you can kind of see that if you even watch how fast they're moving, right? You see how they're going faster now, right? So in a parallel circuit, we get what appears to be a strange result. We get that in a parallel circuit, more resistors makes the current increase. Why? Okay. Well, remember, let's assume we still have this 9-volt battery here, right? What happened is that this 9-volt battery is making everything over here have 9 volts. So I got 9 volts there, I got 9 volts there, and everything over here is 0 volts, 0 volts, 0 volts, right? So whereas in the series case, right, the voltage had to split. Kind of the 9 volts had to be split between the two resistors. In a parallel circuit, each resistor gets the full 9 volts, right? And so each resistor has to pull its own current, which means that if I want to pull the same current here and here, I have to have twice as much current there, right? So I have to have twice as much current coming through the battery in order to pull current through these two resistors, right? I'm going to say this another way, right? What I could say is in a parallel circuit, all elements, I'm just going to say all circuit elements. When I say a circuit element, I mean a battery, a resistor, a bulb, whatever it is. So all circuit elements have the same potential difference or voltage. Everything in this circuit has a 9-volt potential difference. That's not the same in the series circuit, right? In the series circuit, this battery had 9 volts, but each of these resistors only had 4.5 volts, okay? I do want to point something out, though. Let me go back to my animation. You should see, so I got 2.9 amps going through the battery, right? How many amps do I have on this branch? 2 amps. You want to guess how many is in the other branch? If I have 2.9 total, and I've got 2 amps here, what do I have here? 0.9. Does that make sense, right? It should make sense because this plus this should equal that. I must have 2 bulbs that are not the same resistance. Let me check. Yeah, if I make them the same resistance, I should find that, let's see here, I got 4 amps here, 2 of the amps go this way, 2 of the amps go that way. Does that make sense? So you have 4 amps and then the amps split up when they get to this junction. 2 of them go this way and the other 2 of them go that way. All right. Now, what I want to look at though in the series circuit is, in the series circuit, no matter where I go, right, I have 1 amp in this circuit. No matter where I go in this circuit, I have 2 amps. So there's one other thing that I want to add to our notes, and that is that in a series circuit, all elements they don't have the same potential difference, but they have the same current. So in a parallel circuit, all elements have the same voltage or potential difference. In a series circuit, all elements have the same current. This makes sense. You can kind of think of it as a traffic jam. There's only one path. There's only one lane for the charges to go. So if one backs up, they all back up. They have to all go at the same speed. Okay? Now, there's something else called equivalent resistance, right? So equivalent resistance needs to take into account the fact that if I add more resistors to a series circuit, there's more total resistance. But in a parallel circuit, it's like there's less resistance because I'm making the current go up. So there are 2 equations that we're going to use. In a series circuit, the equivalent resistance is equal to just all of the resistors added together. So I write it as Req equals R1 plus R2 plus dot, dot, dot. In a parallel circuit, there's this weird formula. It's an inverse formula. We're going to say that 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, or plus dot, dot, dot. Right? Maybe in another video, maybe in an optional video, if I get a chance, I'll derive these for you. But for now, we're just going to say what they are. And I just want to do a couple examples. So let's say that I have I'm going to do one example. Let's say that I have 3 resistors. Let's say 4 ohms, 5 ohms. Let me think about the math. Math is easy. Let's do 3, 4, and 8 ohms. Can I do that? I'll do 3, 4, and 5 ohms, right? So I'm gonna find the equivalent resistance. So here's example 1. I'm gonna find the equivalent resistance. Let's say I've got a 9-volt battery, and I've got, this is going to be a series circuit. And I'm going to say that this is a 3 ohm resistor, a 4 ohm resistor, and a 5 ohm resistor. Okay? So this is a series circuit, so how do I find the equivalent resistance? Well, I just add them all together. R2 plus R3. So in this case, it's 3 plus 4 plus 5, which is, I can't do math on the spot, 12 ohms. Right? And then if I wanted, I could also find the current by saying, okay, I know that V equals IR, Ohm's law. So I can say 9 volts equals the current times 12 ohms. And the current should be 9 divided by 12, which is 3/4, so 0.75 amps. Okay, so that's how to do find equivalent resistance in a series circuit. In a parallel circuit, we got to be careful. So if I were to do this circuit where I had 9 volts, but I had my circuits like my resistors like this, where I've got 3 ohms, 4 ohms, 5 ohms, right? Then what I have to say is that 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So that's like saying 1 over the equivalent resistance is 1/3 plus 1/4 plus 1/5. Let's think about what this is why I was trying to make it easier. Let's think about what the common denominator here is. Is it, it's not 20, it's probably 60, isn't it? So this would be like, what, 20/60ths plus, let's see, 4 times 5 is 20, so 15/60ths plus 12/60ths, is that right? There might have been an easier one to pick. It might be a lower common denominator, but that's fine. Okay, so this comes out to be 35/47/60ths. Now you got to be careful because a lot of times people would like find what 47 over 60 is and say that's the equivalent resistance, but that's not quite right, right? You actually have to take the reciprocal, so the equivalent resistance should be 60 over 47, which comes out to be 1.28 ohms, right? So what's that saying? That's saying that my equivalent resistance is lower than any of these resistors, which makes sense because we just saw that when we add more resistors, the current increases. Increasing current is like saying that the resistance decreased. So this is equivalent resistance, and then if I wanted to, I could go on. I'm not going to, but I could do V equals IR to find the current again. Okay, so that's the basic idea of equivalent resistance. There's a fairly short check for understanding. We're going to do complex circuits on Wednesday, and then Friday is going to be a chance for you to do some quiz corrections. And that's all I got for today. Have a good day.